Okay. So let's say a generalized case, generalized equation. Let's say you have A plus B gives C plus D. Then how do you calculate the EMF of the cell, or the cell potential for this equation?
If I am not wrong, EMF E naught of the cell minus
Yes.
RT by NF log of the concentration of reactants, no, products upon reactants.
Products upon reactants, absolutely. Concentration of C into concentration of D upon concentration of A into concentration of B. Okay, so this expression, which helps you calculate the cell potential, is Nernst equation.
Ma'am,
yeah.
Sorry. So there's one more equation that you did last time above the Nernst equation. It's the half reaction. I think half reaction, like one electrode ka thing.
Correct.
Yeah. So that's not the Nernst equation.
No, that is partial Nernst equation.
That is also, yeah, that is Nernst equation. And instead of calculating your reduction half, oxidation half separately,
you can use this method to do it directly.
Yeah.
Okay. So that is also Nernst equation, but that's only half of it, or only for half electron.
That's for reduction half, oxidation half. Now, usually if you want to calculate cell potential, you have your main formula, right? So you get E cell by subtracting like E cathode, or reduction half minus
E anode.
Right? So applying Nernst equation, E cathode is again E naught cathode minus RT by NF ln the reduction half of it. Then E anode is again E naught anode minus RT by
that will again become common, and then you'll get the same. Okay.
So when you basically add or do the subtraction E cathode minus E anode, you will essentially land up at this particular equation. Okay, so that's the reason I've given this equation directly, but that's essentially the derivation. From the individual half reactions, you add them to get this. Okay. So what do you guys have? Oh yeah, for the sake of calculation, you can modify this as E cell equal to E naught at standard conditions minus
0.059.
Yeah. So 0.059 if you are measuring it specifically at 298 Kelvin. Otherwise, depending on the temperature, the value changes. Okay, so you get 0.059 by N into logarithm to the base 10, the concentration of products upon reactants. Okay. So do you guys want to do some questions based on this, or
Miss, last class we solved questions.
Direct questions ho gaya na? Okay. So let's do directly. Let's look
electrochemical cell and Gibbs energy.
At like what's the relation with the equilibrium constant and the Gibbs energy part of it? Okay. All right. First, do you remember what is an equilibrium constant?
K.
K, yes.
Yeah, it's the what is it? Just a second.
Equilibrium constant.
Concentration of products by reactants, right?
Yeah. So if we consider the same reaction that we're looking at over here, how would you calculate Kc for this equation?
The same, the variables that you've written at the right. C by
concentration of C power C.
Concentration of D by
D by A and B.
Okay. What happens, like equilibrium constant is relevant at equilibrium alone. So what do you mean by equilibrium? What happens during equilibrium?
The rate of the forward reaction and the backward
Reaction is
reaction
equal
is
to
the same.
the backward reaction.
So rate of the forward reaction equal to rate of the backward reaction. If forward reaction is like whatever is happening in the forward reaction is same as whatever is happening in the backward reaction, in that case, like what do you imagine is happening electrons wise, like current wise? So you set up a cell and whatever, so there's reaction. So as when the reaction is happening, the electrons are flowing, right? Like whatever flow of electrons is there in the reaction, that's what we are capturing as electricity. Now, if rate of the forward reaction is equal to rate of the backward reaction, what will happen to the net cell potential? Like, will there be any current flowing through this thing? Like, will that be unchanged? Will that change? What's happening?
It can't be zero because the current has to keep flowing in order for the reactions to take place, right?
Yeah. In order for
Logically, it should remain the same.
Why?
Like it should keep flowing, like that remain the same.
Consider
Yeah.
the same thing. Zinc plus copper 2 plus gives copper plus zinc 2 plus. So at the beginning, you have only zinc and copper ion, so the forward reaction is going to take place. This happens, and when this happens, you see that there is, oxidation to zinc, reduction to copper, and the electrons are flowing. But slowly, as this concentration starts increasing, at some point, like towards the end of the reaction, or like at some point, because these ions are also existing, the backward reaction also can take place. So we define equilibrium when rate of forward is equal to rate of backward. So then, when forward reaction is taking place, zinc is losing electrons, copper is gaining them, and those are the electrons we are capturing as current. When the backward reaction takes place, copper is losing electrons, zinc is gaining electrons, so this is going to happen in the opposite direction. So when rate of this side is equal to rate of that side, will there be a potential difference created between both the ends?
No, ma'am.
Then what will the value of E cell be?
Zero.
Zero.
Zero. Yeah, so that's why.
Okay.
So, which means that at equilibrium, what happens to the Nernst equation?
If E cell is zero,
So put 0 there, will be equal
so
to
zero. Oh, so electrode potential at STP condition will be equal to RT/NF log of Kc.
RT by NF ln concentration of products.
Oh, can we not write Kc, ma'am?
That's the next step. I'm just going step by step.
Oh, okay, sorry.
Concentration of B. And because this is the equation we are considering at equilibrium, this value, concentration of products upon concentration of reactants, will be equal to Kc. So standard this thing is related to equilibrium constant in this equation. NF ln Kc. Yeah. And if you want to make it usable for your calculations and all, you can write it as E naught cell equal to 0.059 by N log Kc. So, and again, you need to be careful. This is at 298 Kelvin. We put temperature ka value as 298 to get 0.05.
Just a minute. Ma'am. Yes, ma'am, done.
Hello, Ansh, what happened?
Because I'm telling you, he fell asleep.
Is that true?
I wish, but I had gone out somewhere. I came back at 2.
Oh. Since it was Saturday and it's like, okay, you came back at 2 p.m.
I come back at 2:30 from my fitness class and I'm still on time for class. That is not fair.
Not everybody is as punctual as you, Dhriti. Sorry. You should be happy.
Like, are you back in Mumbai now?
Oh, I am very happy.
Yes, ma'am. Yes, ma'am. I came back. When did I come back? A week ago.
Okay. All right. You missed the beginning part of it. We were revising last week's, Nernst equation, and then how it relates to the equilibrium constant is just what we've done.
Done, man.
Yeah. Shantanu, you done noting this down?
Just a second.
Okay, let me know when you're done. Ansh, you can go through this and then just leave some gap and then you can watch the recording later to catch up. Yeah.
Ma'am, I'm almost done actually. Not too much to write, so.
Okay. All right, Shantanu, let me know when you're done and then we'll go to the next part.
Can I just get water by the time these guys are done writing?
I'm done, man. I wrote the entire thing.
Okay, cool. Also, like you guys carry your phones with you, right? So if you were expecting that you're going to be delayed or something like that, at least drop a message so that, like we're informed, like at least we can plan if we have to start the class late or, how to go about this. Okay. Dhriti, I think you are muted in case you're...
I am just passing comments which cannot be said out loud, so it's better I'm muted. I'm in that mood today. Sorry.
It'd be nice if people had that mute option in real life also.
Oh no, I know, I feel you, miss. I really feel you, but it doesn't, life can't go according to you, so we gotta deal.
Yeah. All right. Shantanu, done? How much, where you at?
Yes, I'm done.
Okay, awesome. All right. Now coming to relation of like cell potential with Gibbs energy. Do you guys remember what is Gibbs energy? Also called Gibbs free energy?
It's the only way where you can tell whether the reaction is spontaneous or not.
One use of Gibbs energy, yes, for sure. But what is it? Like when we're saying it's energy, it's like a physical thing, right? Like you have potential energy, kinetic energy that way. So how do you, what is Gibbs energy in a reaction? Like how can you explain or visualize it?
So in my head, Gibbs energy is basically the energy required that's entropy. Sorry. Like randomness, but like entropy and randomness, yeah.
Absolutely. Like Gibbs energy combines the reaction enthalpy along with the entropy
The
aspect,
entropy.
right? So it's essentially a measure of the total energy change that is occurring in when a reaction takes place.
Okay.
Like not just heat energy, not just, like it's the whole complete energy change. That's that sort of a thing. Okay. So delta G represents that energy change. And yeah, so that in turn relates to what you said. Like if delta G is negative, then overall energy, like entropy plus enthalpy, is reducing. So that means more stability. So reaction will be spontaneous. It'll be willing to take place. Otherwise, it's the other way around. Okay. Now, how do we relate it like in electrochemistry? Like when there's a redox reaction happening, and electrochemistry is all about getting electrical energy from chemical reactions, right? So this is how you can relate both of these. Okay. Now, when a reaction takes place, so in a reaction, let me write it this way. In a reaction, specifically redox reaction, when we are talking about electrochemical cells. So essentially what is happening is the chemical energy is converted into electrical energy, right?
Yes, ma'am.
Which means that now this chemical energy, we're talking about, this relates to the Gibbs energy. And when we're doing like, why are we producing electrical energy? So electrical
Due to
energy,
electrons.
yeah, movement of electrons, and then that does work for us, right? So this we can interpret it as the electrical work done by the cell. Yeah. So the chemical energy, like whatever is energy changes are happening when the reaction takes place, that is being converted into electrical energy. So energy changes taking place, the chemical energy available for doing this work is your Gibbs energy, and the electrical energy that it is being converted to, that can be interpreted as the electrical work done by the cell. Electrical work done matlab work done in like moving the electrons. That's electricity. Okay. Do you guys remember the relation between work done in moving some amount of charge? What is the formula associated with that?
Q by V?
Work done equal to W equal to Q by V, or
QV.
yeah,
QV
Sorry.
multiplication.
I sort of,
the potential energy that's like opposing it or whatever, right? So from this, if you apply it to this particular situation for a cell, so this is essentially the work done by the cell is equal to, in the cell, what is the potential difference?
the electrode potential,
The EMF, like the
EMF of the cell.
yes, into Q is how much charge is passed.
Charge.
Yeah. Okay. And because whatever electrical work is being done, that is coming from Gibbs energy. So we can equate work done by the cell, the electrical work done is also equal to the decrease in free energy. Law of conservation of energy. It has to come from somewhere, it's coming from Gibbs energy. Okay. Now let's continue this thought. So decrease in free energy like the maximum work that a cell can do is essentially it can use up all of the different like energy, Gibbs energy that is produced in the reaction. So that will be equal to delta GR, the Gibbs free energy of the cell. If all of it is converted into electrical work done, let's what do you
No,
call
ma'am, I'm sorry. Could you come again? I sort of lost what you were saying.
Yahan tak you clear?
Ha.
Right? So let's see what is the maximum amount of electrical energy that a cell can produce.
Okay.
Maximum amount of work matlab it can use up all of the Gibbs energy that
And convert all of it to
into
electrical work done. Okay.
So work done by the cell, I'm putting delta GR on electron because it's using up all of the Gibbs free energy is equal to now V into Q. So let's substitute the values that that make sense in this situation. All right. EMF is your cell potential, so that will be E naught of the cell into the amount of charge passed. So in an electrochemical cell, how can you calculate how much charge is passed? Like during
number of electrons into the with 1.6 into 10 raised to minus 19 coulomb.
Correct. So the number of electrons, like going by this convention, N will be the number of electrons and the conversion factor is Faraday's constant. So the total amount of charge
So NF
will be NF.
Oh,
So this
okay.
is the relation between Gibbs free energy and the cell potential. This is the equation. So that is delta GR is equal to, so there'll be a negative sign associated with it because this is the decrease in Gibbs energy.
Okay.
So minus NF.
Yeah, miss, all the Gibbs free energy is being utilized completely in order to convert to electrical energy. Why are we taking delta RG? We can also take 0, right? If the, I don't know if that's making sense, but
No,
like
zero
if all
zero.
the energy is okay.
So if it is equal to 0, it means that there is no energy available for doing this.
Oh, okay.
Yeah.
Okay, got
So
it.
whenever delta GR is available, we're using that.
Could you go back for a second?
Note it down. There's a slight mistake here. This shouldn't be E naught because we are not considering standard conditions. Delta G equal to NFE. Correct. Note it down. No. Okay. So this is related to Gibbs free energy. So one slight thing, if you consider at standard conditions, STP conditions.
So it'll become E naught.
Yes, this
Cell
is delta
potential,
G naught, this is E naught. So delta G naught are equal to minus NF E naught. So this is one way, if you know the cell potential, you'll be able to calculate, like you can figure out the Gibbs free energy. Next, another this thing, like relating delta G to, okay. So next coming at equilibrium. You have the relation between E naught and the equilibrium constant, right? So substitute that. So you get delta RG naught equal to minus NF into, iska value kya hai? What would be the E naught cell at equilibrium? Ansh?
What would be the value?
Like we had the formula, right? How do you calculate E naught cell? What is the relation between E naught cell?
The value is delta G.
IT No, RT,
Yeah.
NF, LN,
RT.
KC.
Yeah, that.
Like
Because it's
abhi
at
likha hai na,
equilibrium,
like
right?
you can check, like turn your page back, check.
Ma'am, so NF will
Log.
get cancelled.
RT by NF.
Ln
Log
of KC.
KC.
Non-KC, right? So NF get cancelled, which means that Gibbs free energy at equilibrium at standard conditions will be equal to minus RT log KC. Now, does this expression look familiar?
Yep.
Oh yeah.
I think I saw it.
Yeah.
When we
Okay.
were doing equilibrium, we had done this. Yeah. Okay. So all the quantities like your electrode potential, Gibbs free energy, equilibrium constant. So you have the relation between all of these quantities. Now let's do a bunch of problems relating to this. Let me know, like just go through all the formulas once, and when you're ready to solve questions, let me know.
I'm only from
Ready,
equilibrium
ma'am.
constant or even before that.
Sab kuch. Topic practice 1, entire of it.
Acha, okay.
Yeah. Topic practice 2 deals with conductivity and all. So all the topic practice 1 questions are related to this. Okay, so
Oh my god, my laptop is not charging.
Yes, ma'am, done.
Nernst equation, calculate equilibrium constant. Okay. There you go. So do question number 9. So it is 310, right? So how long? It's a direct question. You're given E0. You need to calculate Kc. Only the calculation will take a lot of time. So see if you can finish it by 3:13. 2 minutes.
Miss, I don't get this logic. You said it's a very long calculation and you give us only 2 minutes.
This is a lot of time.
Which question?
Question number 9, Shantanu. You've noted down all the formulas, right? So you can refer to the formulas until you're able to memorize and get a hang of them.
Yes.
Ma'am, when you take log to the other side, what does it become?
E power. Or
Okay.
you need to do, like, if you're looking at calculation, anti-log देखना पड़ेगा.
Okay. Ma'am, it's a lengthy calculation.
Yeah. You have a whole minute. Okay, I'll also do it with you guys.
Miss, I got the answer, but it's very, very weird.
You see the options here. Is it not matching the options?
No, it kinda is.
Right.
Is it right or wrong?
See, I will have to check. I have not calculated. Let me check the solution. Yeah, Nriti, you got it. That is correct. Oh, Mitali, I answered wrong. I'm sorry. So when you take log to the other side, if it is a natural logarithm, that becomes e raised to the power. But otherwise, it will be 10 raised to the power. That
Oh, okay.
like mathematically, that's what like powers ka inverse function is logarithm. Like the way multiplication
Okay.
are inverse to each other, that way logarithm and power are inverse to each
Yes, ma'am. Just a second.
other. Cool. And Shantanu, where you guys at? Last step logarithm ke liye- actually what is, are you guys allowed to use calculators now that you're doing like now that your questions are online and all of that, or are you still expected to use log tables and do it all manually?
Ma'am, our chemistry teacher had said that the CBSE has like forbidden log tables. Last year only they had said.
Oh,
Ma'am, I don't think so we are taught log in school. At least I am not taught.
No, we are not taught, and
Neither
yesterday
am
we
I.
provided log and anti-log tables. We were just told last class Friday ko by our Shri teacher.
oh, that you won't be given problems related to logarithms.
Wait, I'm confused.
Yeah. So
No, we will be given problems related to log, but either the value of the log will be given or the log table will be provided.
But we haven't been taught how to use log tables.
exactly.
Yes, our teacher taught us.
11th
She
one
did?
had a lot
What
of
the
Yeah,
hell?
Fatma.
What is this partiality?
It's not
Exactly.
partiality. We just told Miss, we don't know, we have not learned. So she took
Yeah,
15 minutes
our teacher,
out
No,
of her beautiful
we
when
time,
get
our
and
teacher,
she taught us.
we get
when we
pushed
tell
over
that
to
to
physics
our teacher said
teachers.
that we send you a YouTube video, and that she
No,
didn't.
for us it was pushed over to
No,
physics
she said she
teachers.
would send us a YouTube video, but she gave us a gist and she sent the YouTube video, I think. I'll forward the link.
हाँ अपना उतना भी नहीं हुआ.
Okay.
Sad life.
If you guys want to learn, I can check things out and I can
Yes, ma'am. Can you please
Yes, ma'am,
send
please,
me?
ma'am.
class, like I have forgotten. Last time I used log tables, it was exactly your age.
I don't know if that's supposed to be like insulting or that's supposed to be a compliment that, once it should be a good thing that once you do finish log in 12th, you're not supposed to touch log ever.
Because engineering may you can use
Then why we taught logs at all? What is this? Logicless. Stupid.
Do trigonometry, logs, these
Hey,
stuff.
trigonometry is still used. Trigonometry is still
Where
used.
is it used?
Engineering
Where?
is still used.
Yeah, it's used. Like I know for a fact, animation industry may they use it. I'm sure I can
And
imagine
BTech also they teach more trigonometry and stuff.
trajectories, even military defense, like calculating trajectories and all of that stuff. I can imagine it being used.
Do BBA, why will they teach trigonometry?
Astronomy uses it. I know that because
There you go. One
some
more.
contacts, something like that. But I don't know which other engineering field uses trigno.
Civil engineering,
Civil. There you go. Another
mic
one.
drop.
Even like things where astronomy may like you need to figure out orbital trajectories and how should the rocket move and all of that, and similar application applied to different scenarios. Like you want to calculate how a missile moves, especially now we are getting into AI, right? So if you need to direct AI without manually controlling it every time, you need to have these calculations and measurements in place. Yeah.
Riti, if you do BBA after 12, why do you expect to have trigonometry at all?
My point exactly. I don't see the point of me studying trigonometry or chemistry
You
or
chose science, and not
biology.
our fault.
Listen,
I didn't take it by choice.
listen.
In school, my aptitude was commerce, but then I still
Again,
chose
not our
science.
fault.
Yeah, that was my fault.
See, it is definitely an advantage to you, Dhriti, because even if you're doing hardcore just business administration, you still need to talk to your other, be it clients, vendors, whoever. right? You can.
My dad said the same thing.
A
I need to have knowledge. If someone is going to put forth a nuclear something to me, I need to know how it works to, at least the base of it.
like you can see it in action live, like the whole controversy around vaccines and like the whole healthcare and things like that. Like you don't want to end up like that. So anyway, coming back to this, Dhriti and Ansh, you have not sent. Mitali has sent the answer.
I sent.
Oh, wait,
Hello.
wait, wait, wait.
Yeah, Dhriti and
I sent the answer.
I said Dhriti and Mitali. Ansh and Shantanu. Ansh, okay, has sent it. You got it.
And
Shantanu,
is it correct?
yeah, all of you are correct. Shantanu, what's up? Okay, Shantanu has also sent it. Awesome. Direct application formula hai. Just put the values. I'm glad you guys got the value of n correctly. 2 electrons exchanged. Okay. Next, representation of galvanic cells. Do you guys remember how to represent them?
Yes.
Okay, quickly send it off. Like you just
Type. Okay, wait. Just a second.
Can we do like this one person at a time and they answer it? Because it's too boring to type. Sorry, but
यहाँ पे how can you say the answer? This is representation. How do you write it? To do it for this, and whenever it is like, well, we can.
What question are we doing again?
Question number 11.
How do I send it to you?
Direct message. Oh, did you write it in your book?
Yeah, forget it. I'm sending.
What way you can send it?
No, I'm sending.
You can use like your backslash, or you can use that. ये वाला. Wait. Enter के ऊपर जो रहता है.
Where is my backslash? This.
Question mark. Whatever that. Sorry, that's forward slash. Backslash is that other.
Ma'am, like 30 seconds to type.
Yeah. I did that. You should take time for typing it in. Otherwise, oh, and another thing you need.
Wait, so we send you the picture of the cell or we just type the whatever?
Either or. If you've written
Or
it, send it to me on WhatsApp. Or you have the option of typing it here directly also. When you type, you can type something like ZN slash whatever, then slash. And then
You're giving the answer.
FJ. I'm just giving you the format. Like if you're typing it, use the slash over here. Yes. Okay.
Is it right?
Yeah. One tiny thing, you don't need to mention anode salt bridge. Like that is just to explain that, oh, that part represents.
That is to explain it to me.
Yeah. You don't have to write.
Okay, I won't in the next, whichever.
And add the states. Like if you have.
Aren't they obvious?
Mention it because.
No, it's a compulsion to mention states. Like if you
Yeah, I
don't,
know it
you
is
might
one.
as well look. Yeah.
Yeah. So Diti and Mitali have sent it. So Ansh and Shantanu. And Mitali and Riti, you guys look at question number 13.
1-3.
Yeah. And Shantanu, what's taking you guys so long?
Just a second.
Hmm. Okay, Shantanu sent it, and she sent it on WhatsApp. Yes, Shantanu got it. So you guys also look at question number 13. Oh, Shantanu, sorry, Ansh, you have drawn the cell. When the question asks represent the cell, I have put it here, right? So this is the cell representation. Like we did this last class, remember? This kind of representation.
Mrs. entered the answer for 13.
Big rain. Yeah, but Ansh, type it out this way or write it and send a picture. So just for your understanding, whenever they say represent the galvanic cell, you don't have to draw the picture of the galvanic cell. You can directly just do this. Cell representation is a thing, like it's a section so that you get familiar with this representation. Mitali and Dhriti, oh, both of you, the first part of the question, both of you sent like opposite stuff. The second part of the question, yes, when E naught is 0.
Could you go over the first part of the question?
Miss,
Because I'm
E
not
naught
sure.
is equal to 0.0591 upon N into ln K.
Yeah.
I mean,
Yes.
so if K is less than 1,
Yeah. So that logarithm ke baad ln will be less than 1, matlab it's going to be some fraction. Like say it is
yeah,
2 or something.
1 by, yeah, half.
So then if you convert this into like a regular logarithm to find the value of it. So
You get minus, you get the minus sign.
yeah.
Oh, so it will be negative and not positive. Okay, ma'am.
Yeah.
This gets converted into ln 2 power.
You know, Mitali, I feel bad for you.
And when you have -1, this gets multiplied over here. The overall value becomes negative.
She dropped physics. No, she dropped maths. Yet she has to do maths in physics and chemistry.
At least it's not all of maths, like a very specific.
Miss, log is literally math and it is very boring.
At least she doesn't have to do matrices and all of that.
Yeah, Miss, you know how to rub salt on the wounds.
I have perks,
I've been through it.
and
Like,
but it hits me hard. But then YouTube to the save. I can't do anything else
Yeah.
about it.
well, for physics, chemistry, you need to know these 3-4 functions. Like you need to be okay with trigonometry. You need to know calculations with logarithms. Apart from that, what else do you know?
And you need to know vectors and derivation. No, derivatives.
Differentiation.
Differentiation. It's half of maths.
But you don't have to do like differential equations. Like, yeah, it's not advanced stuff. You just need to know how to do these things. It's fine. Okay. Ansh, did you get the cell representation?
I'm 1 minute.
Okay. So cell representation, whenever we say cell representation, you have to, it's going to be of the form like the reduction half, the oxidation half separated by this two lines which represent the salt bridge, and then you have the reduction half. So this will be written as oxidation half में क्या हो रहा है? Zn solid getting converted to Zn2 plus aqueous, separated by salt bridge, and then reduction में you have Cu2 plus aqueous getting converted, separated by a single line here, to Cu solid. Okay, so this, like whenever you're asked question about representing a cell, this is what it's your answer. This is the format of your answer. This is what you need to give. Okay. Okay.
Yes, ma'am.
All right. Then did you guys look at question number 13? Like we kind of discussed it also. Do you follow what to do, how to go about it? Yes, no? Anyway. Oh, okay. Question number 19. So calculate the EMF of the cell in which the following reaction takes place. So you're given the reaction, and you can see you're given the concentrations also here. And you're given that E naught cell standard conditions pay, it is this. So given concentrations, you're given the reaction, and you're given E naught. So based on this, how, like what would you use to calculate the EMF of the cell?
So the concentrations are given. We use the formula. Just a second. We use the work done wala formula, right? No, not the work.
You need to calculate EMF of the cell. So you need to calculate E cell equal to.
So we use the Nernst equation. E naught cell minus RT by NF ln of the concentration of reactant by product. Ma'am, for solids, the concentration, I'm just confirming, for solids, the concentration will be 0, right?
Correct.
Yes, thank you.
Hello. This will take some time, 3:32 hai na? Try and finish it by 3:35, 3:36. Yeah.
Miss, you just gave us so much time.
Yeah, इसमें time लगेगा calculate करने में. Logarithm के लिए use your calculator.
Thank you so much. But wait, I don't have a scientific calculator.
Phone है ना, like phone में you can find logarithm.
Yes, ma'am, I'll do that.
No, this is an NCERT question.
I'm sorry, my equilibrium basics is really bad. The way we write the concentration, it should be 0.02 into 2, right? Raised to 2.
Yes. That's
okay.
And in this situation, Nernst equation may you have the value. What will be the value of N? Like what's
2 electrons.
Yes. So 2 electrons, Ni2 plus. Even though Ag is plus, you have 2 of it, 2 atoms or ions of Ag. So overall number of electrons is 2. Send your answers over the chat. I'll just be right back. Okay. Dhriti has already sent answer, and that is the correct answer. You got it.
Yeah, hey, I got it right.
You sent it long back, like she's done it months ago. I was
At
fast.
34.
Yep. Good stuff.
It's just 1, 2, 3, 4, 5. 5 steps.
Yeah, it's just calculation. Like once you identify what values to put, after that it's just calculation. Yeah. And Chandni, you guys solving? Are you stuck somewhere? What's going on?
I'm sorry, ma'am.
Solving. Okay. Ansh, what about you? Ansh also has sent in. Yes, correct. Got it. No, Mitali got a different answer. Kaise?
Must be 100% a calculation error.
Okay, so construct Nernst equation. So what did you do?
I did that.
0.05 minus 0.059 divided by 2 into log product is 0.26 divided by 0.002 ka square. Is this what you started off with?
Yes, ma'am.
So check it number 1. So first, this you can figure out. फिर ये logarithm calculation you can figure out. And then
Is it 1?
No.
Okay. I'm doing something wrong.
It's less than 1 but close to 1.
I'm getting 1.
Are you getting like straight away 1, or did you like round it off at some point?
Rounded off to 1.
Okay.
No, wait. This is what I'm getting. No, I'm getting straighter. This is 1.00. This is what I'm getting. 1.0 blah, 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 blah.
Oh.
And there are like a lot of digits.
1.0, after that, what do you have?
1.002739 blah, blah, blah. Still a lot of digits.
Shantanu, where are you at for calculation?
Mom, what question was it? 19.
Oh, you have your book then.
Yeah, no, I'll check what I did wrong.
Shantanu also got it. So 0.915916 के आसपास आना चाहिए.
Yes, ma'am, calculation error. Log का calculation error. 0.6. Yes, ma'am, I've got calculation error. I haven't taken the 10 raised to 4 in account. So against it, I don't know how it's affecting the calculation, but somehow it is.
Cool. So that part you need to be careful. Writing Nernst equation. Wait, we can go a step. Another one, same like this thing. Just to get the hang of writing this one also. Question number 24. Calculate the EMF at 25 matlab, ठीक है, 298 Kelvin itself. You're given this thing with the concentrations and oh, it's all 10 raised to the power. So your calculation also becomes so much easier. And they've also given log 10 raised to the power n. I will also do it with you guys. There is one twist. You build it as cell representation, right? So you need
Yeah, so if we convert it back to the 2 in AG is missing.
you need to be careful with how many electrons and also like that part. Right. Anyone who solved it?
Just a second, I'm calculating.
Jyoti and Shantanu, what about you guys?
Solving, ma'am.
Yeah, like this calculation is so much easier than the previous one. I thought you'd answer faster.
I did a calculation error, so please solve it. Miss, I sent you the answer.
Yeah, chat pick, yeah?
Not WhatsApp. One second. I didn't. Sorry.
Abhi, check calculation again.
Ma'am, who, ma'am? I'm sorry.
No. Why is this so troublesome?
Ma'am, even I sent it on chat.
No, the answer that you think not right.
Ma'am, I can't hear you properly.
The answer both of you have sent is not correct.
Oh, okay. We'll check again, ma'am.
EMF of
Miss, we start with E naught cell minus 0.059 by n log Cu2 plus upon Cu plus
upon n. What is the number of electrons in
2
into
Ag plus
10
2
raised to minus
10 raised to minus 3 square
minus 1 upon 10 raised to minus 3 the whole
3.
square.
right.
Yeah.
Okay.
Yeah, that's exactly what we started with.
Yeah.
As it is. 0.059 divided by 2 कितना होगा? Answer is get 0.05
0.0295.
is correct. Into, if you simplify this, 10 raised to power minus 1 divided by 10 raised to power, this becomes 6. So
Yeah, so upar jaake will become 10 raised
10
to 5.
raised to 5.
So the answer will be 5. Yes, ma'am.
0.2.
That's exactly what I did.
Okay. So 0.46 minus. Yeah, what is the answer of this multiplication?
0.1475.
Yeah, ma'am, that's exactly what I did. 0.46 minus
Yeah, miss, I got the same
0.1475.
answer. Oh
And I've
no,
got
I did some
0.04.
calculation error in the last step. It's 0.31, not 61.
Okay. But Dhriti, you got
What?
it. Really,
No, wait, what? Yeah, wait, 0.4. That's exactly what I did.
align the decimal points.
Ah, okay, okay. Rookie error.
And Shantanu, why did you guys take so long? This is much easier than the previous one. Where were you guys stuck? क्या हो रहा है? will be 0.3125 volts. That's the answer. Anj, are you there? Not able to hear you in case you're speaking, Ansh. You're muted. Yeah, you're under mute. सुनाई नहीं दे रहा है. Okay. So अगर network issues हो रहा है तो like see if you can restart.
Yes, ma'am, I got the answer.
Alright, cool. Shantanu, what about you? Where are you at? क्या हो रहा है?
Yes, I got the answer.
Got it? Okay. Cool. इसके बाद one last question. We'll do one based on Gibbs energy. 4 o'clock. Let's see if we can start with conductance. Okay. We'll go with a simple question here, NCERT in-text question. Look at question number 30. The cell in which the following reaction occurs. So you have the cell. It has E0 cell equal to 0.236 volts at 298 Kelvin. So temperature is standard. You can go with 0.059. Calculate the standard Gibbs energy and the equilibrium constant of the cell reaction. So one, you need to calculate delta G naught. Excuse me. Sorry. And second, you need to calculate the equilibrium constant Kc. Yeah.
Ma'am, is this standard? Wait, if it's standard, then K, sorry.
98 Kelvin, no? You have the relation between all of the things, delta G naught and E naught cell also you have the relation. Kc and delta G also you have the relation. So it's a direct application of the formula. The only thing you need to be careful is the value of N. Okay. All right. So before you start the calculation, send me what value of N you're taking in this thing. So all four of you send it over chat.
Yes, ma'am, just a second.
Are you sure about that, Mitali? N is the number of electrons ka exchange that is involved in this reaction. How many electrons are being exchanged here? Dhriti got it. So pick either the oxidation or reduction and see what is the total change in this thing. Ansh, that is correct. But N is literally the number, right? So you don't need to use, like, it doesn't have a sign, like it's going to be positive. Mitali, now you got it. That is correct. So Shantanu,
Yeah, ma'am, I sort of didn't take the
number of
the numbers in consideration. Yeah.
All right. Shantanu, just waiting for you. So remaining, yeah, three of you calculate delta G. Shantanu, send N first.
Yes.
because अगर n गलत हुआ तो you'll have to do the calculation, उसमें correction करना पड़ेगा. So. Yes, awesome. All of you identified. Okay. Calculate delta G.
Miss, your screen suddenly turned blank. Can you reshare?
Yeah. So KC के लिए ना, like even if you send me the, what do you call it, the log KC value, that will be fine. If you can, like find the anti-log directly from calculator or elsewhere and send me, that's fine. But if that is like if that's going to take time, if that's some trouble, send the value of log KC, that number. So even if you send me log KC value, let me know that that's log KC, and then I can verify your solution.
Miss, don't we have to use anti-log here?
That's why I said, like, if you got log KC equal to something, send me that number.
7.983.
Yes. बता दिया. If you found out KC, that's okay. That's awesome. But if not, the last step, like log KC ka value, at least you can send that. Just to verify, like उसके बाद anti-log निकालने पे you're going to get the same values. Yes, Mitali got delta G value correct. Joules, yes. Use capital J for joules, okay, next time. I don't know if because it was
No, sorry, because the caps lock, I sort of.
Yeah, just in case you guys didn't know, like it's not interchangeable. Units, capital J represents joules. Have you guys come across conductance before in any chapter in physics?
Yes, ma'am. We just finished the chapter like a month ago or something like that. We're doing capacitance. We came across conductivity.
Conductivity, conductance. Okay. So,
Yep.
so you know the names of the meanings of the terms, what they mean.
Yes, ma'am.
The exact same thing, just applicable to electrochemical.
Electrons in a solution.
Yes. Not electrons, ions in a solution. That's a major difference.
Ions in a solution. Sorry. Ions in a solution.
All right. So we'll start off with the basics. First, you have resistance represented by R. So R is for any specific conductor. What is R?
Resistance. Oh, P L by A. P stands for resistivity, L stands for the length, and A stands for the
Length, A for
cross-sectional
area.
area.
One small correction. It looks like a P, but
It looks like, oh,
It's
for,
fine.
for sorry, for it's
calculate.
easier to remember for
No,
me
it's
when I
rho.
say that P.
So rho is basically R. So like resistivity R is the Greek version of it. Is that. Okay. But as you said, so rho is the resistivity. L is the length of the conductor, and A is the area. So consequently, if you had to define what is resistivity, so resistivity is something that is
Hindrance in the flow of current.
uh,
No, that's resistance.
Resistivity.
dependent on like
Resistivity is the resistance offered by a certain substance.
The material,
so
the
resistivity.
nature of the material.
If you had to define it, just rearrange this equation. So rho will be equal to R into A by L. Okay. So if you had to define it, it's basically the resistance offered by a conductor, which is 1 meter in length and 1 meter square in area. So it's the resistance offered by a conductor. Because look at it. If area is 1 meter square and length is 1 meter, so rho will be equal to R. Like the resistivity will be equal to the resistance. So it is the resistance that is offered by the conductor of length 1 meter and area of cross section 1 meter square. Like make everything else that you can control 1 and you get this one. All right. So talking about conductivity. Okay, before we get there, let's also talk about the SI units. So SI units of R will be
Ohm.
ohm. Yes, this is the symbol, also called ohm. Resistivity ka SI unit will be?
It does not have a unit.
It's unitless.
Why is it unit? It doesn't have a unit. Rho is equal to RA by L, right? R is ohms.
Oh, ohm meter
meters,
inverse. Sorry.
meter.
My bad. But something does not have a unit here.
Ohm meter. No, all of this has unit.
My meter in, okay. Yeah, sorry.
This is resistivity we're talking about. Right? These are like the basics. Now coming to conductivity, resistivity is resistivity.
Miss, in this, didn't something not have a unit?
Yeah, that's exactly what I'm saying. There's something which does not have a unit.
Yeah.
All of these are like- even cell constant.
Okay.
We come across it if at all.
It's something with density.
Current density. No, current density. As a
No,
unit. Sorry.
Okay, three different.
it's related to Archimedes principle. I remember that much.
Oh,
उससे ज़्यादा
It's
नहीं याद
related to what? It's related to
Archimedes
what?
principle.
specific gravity
Archimedes
is
principle.
unitless because it's density relative to the density of water. Let's be talking about specific density. Specific gravity.
Yes, sir.
That doesn't have unit. Usually when you're comparing two of the same quantities, then that becomes unitless. Anyway, so this is all about resistance. Now, if you look at like its counterpart, so resistance is resisting the flow of current, right? It's opposing the flow of current. So when we talk about conductance, conductivity or conductance, they are literally the flow of current. Conduction
It's
is
the inverse of resistivity.
correct. So when we talk about resistance, the counterpart is conductance. So conductance is represented by G, and G is literally the inverse of resistance because its definition itself is the opposite of resistance. So it is the ease with which the current can flow through a conductor. Note this down. You know what? End of the chapter, we're going to do like a summary of all the equations and formulas we come across. This is this thing. So again, related like resistance R equal to rho L by A, right? So just write that down there. Substituted Z will be equal to 1 by
A by
L. A will go in the numerator. Just substituting the value of R. So this particular quantity, inverse of resistivity, that
conductivity.
conductivity. That G is conductance equal to, so that's represented by another Greek alphabet kappa. K into A by L.
That's what kappa is.
Yeah, it's the Greek alphabet.
Ma'am, I'm the chem teacher that we have at school. She calls it kappa.
So, yeah, at the
I
end,
was so confused.
at the end of the year, you guys will be able to read Greek alphabets like just like how you read English. You may not understand the meaning of words, but you will be able to read.
Ma'am, K is used for almost everything. Like if we keep like K in the center and start drawing arrows from it of the amount of constant, like the times it's used.
Oh, K is, you have it for Kelvin. This is the Greek alphabet kappa. Like how
What
A
is the
from alpha,
difference?
K is different from kappa.
But like if we write K, like, is that like a violation?
It looks like a K. I mean, Greek kappa is anglicized into the English alphabet K.
Okay.
But when you look at it in print, the difference gets much clearer.
Oh, okay, ma'am. Got it.
Like small k also looks like this. Capital K looks like your English K itself. Okay, so this continuing, now this new quantity inverse of resistivity we introduced. So K, which is equal to 1 by rho, is called the conductivity. You guys able to see this part of the screen, right? Or should I go to the next page?
No, miss, it's visible.
So resistance ka inverse counterpart is conductance, and resistivity ka inverse, its counterpart is conductivity. Okay. So conductivity, it's also called specific conductance. So don't get confused. Just conductance is G. If it is specific conductance, you can think of it this way. It's basically conductance in specific conditions where A equal to 1 and L equal to 1. So that particular conductivity is called specific conductance. Okay. So let me know once you're done noting this down, then we'll discuss the SI units for conductance.
Done, ma'am.
Done, ma'am.
Ansh, Shantanu, what about you guys?
Done.
Okay. Right. Ansh? Okay. 1 by rho, A by L. Okay. And just like how we define
I'm done.
Okay. Just like how we define resistivity, you can define conductivity also as conductance of a conductor or a solution, which is 1 meter in length and has area of cross section as 1 meter square. All right. Now SI units. There's gonna be a lot. Conductance G what do you think the SI units of conductance would be? Like
Ohm
resistance,
inverse.
ohm inverse is the most straightforward representation. Ohm ka inverse, sometimes you'll also come across mho being used. Literally the inverse of ohm, MHO. Another unit specific to this thing, like for conductance, used is Siemens. S. It's like the
Ma'am, is that like a capital S?
yeah, it's a capital S.
Okay.
It's a Greek engineering, like electronics related company. You have
Ma'am,
Schindler.
isn't Siemens, yeah, like you see it on, what is it called? Electrical boards
Yeah,
in the houses, in schools.
definitely. Now from this, can you derive the SI unit for conductivity? Papa? I'll just write the formula here for your reference. So K or G happens to be K into A by L. So if you rearrange this, K will be equal to G into A by L. So based on this, what would be the units of
Ohm meter.
ohm meter?
No, ohm inverse meter. Sorry. Ohm inverse of meter. Then Siemens inverse. No, Siemens meter. SM.
Oh, A by L, taking it to the other side will be inverse. So this should be G into L by L.
Ohm. Then ohm inverse, meter inverse. Siemens meter inverse.
Yes. Also, you can write it as
SM inverse.
per meter, per meter, or meter inverse if you don't put a fraction to it. Also, write it as multiple. Whatever. Yeah. So these are all the SI units. There's a conversion factor also. You can use either meter or you can use centimeter, depending on the situation and context. So here you need to be a little careful with the units. So conductance or conductivity depends on so one, just like resistivity depends on the nature of the material. It's like an inherent property of the material itself. The second, it depends on the temperature. And three, it depends on the pressure. If it's a solid conductor, then pressure will not become a factor. But when we're talking about electrolytes and all that, then pressure will start to matter. Yeah. Okay. So Dhriti, Ansh and Chandni, you guys done? Can we go to the next part? So far we have
Yes, ma'am.
cool. So these are all like just an overview of the terms that we are going to use later on. Okay, just the meaning, like what they're depending on and all. So one, again, when we talk about conductance or conductivity, it is literally like that particular physical quantity is telling you how easily that material can conduct electricity, right? So depending on the magnitude of that conductivity value, like the numerical value, you have like, if it's a really high value, then that material is called a conductor. And if it's a really low value, it becomes an insulator. Essentially, you'll put it under insulators. So this represents high value of kappa. And insulators, this value is low. And if it is somewhere between conductors and insulators, if it's moderator, not like it's moderate, medium, average, then that becomes a semiconductor. As high, in this case it's low, this is somewhere in the middle. And then you have a special case of material, they're called superconductors. So these have an extremely high value of conductivity, that their resistance is like practically, almost zero-ish that way.
And could you give some examples for superconductors?
So again, this is like a really special case. The most commonly how you get superconductors is certain metals or materials, you cool it to almost like 15 Kelvin. You cool it to like extremely low temperatures. That's when, they start conducting like crazy. That's how we get superconductors. So you get them when you cool like certain metals to extreme low temperatures. This is like theory, in case we given examples and all. Conductors ka examples, you have most metals, graphite, things like that. Insulators, you have plastics. I think is there a table given in your textbook like with different materials, different values of K? Based on that, you can figure it out. Semiconductors, you have like impure silicon, you call it doped silicon. Like you add some impurities to make it a little conducting. Yeah. But okay, now, and then you have electrolytes, like ionic compounds in different concentrations. Pure water, uska K value is like really, really low because the number of ions present in it is really, really low. All right. So then you have different types of conductors, like if they are able to pass electricity through it, depending on how they pass electricity, you have two types of conductors. So the first type of conductors, you have electronic conductors. Also called metallic conductors. So the key is in the word electronic. So in this case, the conduction of electricity, like how the electricity flows, conduction of electricity, like electrical conduction, is mainly through electrons. So if the flow of electrons is causing current to flow, then that's called an electronic conductor. And you can figure out, you can see why they're also called metallic conductors. So metals are able to conduct electricity.
Free valence electrons are the ones that conduct electricity. Yeah.
Of electrons there. So they are the ones conducting electricity. So all electronic conductors, metallic conductors, they conduct electricity to electrons. electronic conductors, because it happens through electrons, so this depends on, so what all will affect the conductivity, do you think?
Temperature,
Temperature for sure, yes. What else?
type of metal,
Yes, we can say the nature and structure of the metal. Like what sort of crystal structure and inherent nature. Then number 3, what else does it depend on? So metals may, it conducting through electrons, right? Where are electrons coming from?
valence electrons. So valency.
Yeah. So it depends on the number of valence electron in each atom. So sodium, it has only one valence electron. So every atom can spare only like one electron. Compare that with aluminium, which has 3 valence electrons. So every atom can spare like 3 electrons, which can carry electricity. Okay. Another major point for this kind of conductor is, so like all the wiring uses metallic conductors, right? So you have copper wires or alloys like nickel and things like that. So let's say, there's a newly constructed house, all the electrical systems, all of that is new. So after like 3 years, if you open up the wires, will you find the same copper that is there, or do you think that would have changed somehow?
No, ma'am, it should be the same, right? Because in a house, all the wirings, you don't change it every 3 years or every 4 years. They're still intact until there's some leak or something.
So an important thing in this kind of conduction, like where it is an electronic conductor, is the nature and composition of the material does not change. So copper will remain copper. It's not going to gain electrons. It's not going to lose electrons. The same thing keeps going on, right? So nature and composition does not change. So it does not change due to the electricity passing through it. Like if you put water on it, if there's like ants or something eating it, then that's a different matter. But it does not change due to the electricity. Like passage of current does not change the nature or the composition of electronic conductors. Yeah. Right. The others, are you guys following? Are you keeping up? Dhriti, Ansh?
Yes, ma'am.
Yeah. Okay. Noted?
Yes, ma'am.
Should we go to the next part?
Yes, ma'am.
Ansh, Shantanu, what about you guys?
Yes, ma'am.
Okay.
Yes, ma'am.
Cool. Now the other type that we'll be talking about, so they are called ionic conductors or electrolytic conductors, is it? Electrolytic conduction or conductors. So this happens like electronic conductors the primary conductors were electrons. They were the ones carrying the current. In this case, what is the conductance due to?
Ions.
You'll see this a lot in solutions like polar solvents, where ions like salts are mixed with that can carry this. Just like the previous thing, okay, what all does this depend on?
Nature of the electrolyte, temperature again.
Yes.
Um,
So when we say nature, it's the polarity and viscosity.
yeah, how easily can it dissociate? So weak and strong electrolyte.
Yeah. Next is the you mentioned temperature, absolutely. Next, what else does it depend on?
Current? No.
Current is what
No.
we're
Yeah, sorry.
one is, yeah, write down like what is the material here. Specifically viscosity of the solvent, nature and viscosity of the solvent, temperature of the whole solution. Nature of the electrolyte itself, like the polarity and all, what we were talking about, how easily will it dissociate, all of that stuff. What else? So the primary things are ions, right? Like what are the different things associated with the ions?
Size of the ions.
Size of the ions, correct.
But ma'am, how does the size of the ion differ? Like
The size relates to, so along with the size, we also talk about the solvation. So depending on size and how solvated it is, like how hydrated it is, that will affect the mobility of the ions. So if the ions can't move because they're surrounded by too many water molecules, or if they are large, if there's, if they can't move with enough speed, then the conductance is reduced compared to ions that have high mobility. One more thing. So when we say ions, like in the case of electronic conduction, we talked about the number of valence electrons available in the atom. So uska counterpart in electrolyte, what could it be? What other quantity could it be?
could you repeat that?
Like in the case of metallic conductors, we said that the number of electrons in the atom also affects the conductivity. Uska counterpart in electrolytes, what would that be?
The number of electrons it needs, or the number of electrons that get displaced during the electrode. If it's like Zn2 plus, no wait, Fe2 plus.
That will tie in with the nature of the electrolyte itself.
Oh,
right?
okay.
What is the thing that we can control in this case?
Amount of the electrolyte.
Yes. So what quantity does that relate to? Like what is the amount of electrolyte per unit volume or quantity of the solvent need?
Volume. No wait, what? Sorry.
Amount of electrolyte or the solute per unit quantity of solvent or solution.
Concentration.
Concentration. So higher concentration, you have a lot more ions. Lower concentration, you have lesser ions. Concentration of the electrolyte. Okay. Yeah, these are all what it depends on. And the whole, like a lot of the next section will be focusing on how it varies with the concentration. Mainly, yeah, this is what we'll be looking at. Temperature also maybe to some extent, I guess. I'll have to check the syllabus. But mainly how conductance or conductivity is affected by the
It's a concentration, yeah. Like strong, weak electrolyte and their concentration, dilution and stuff like that.
Correct. All of that stuff. Okay. Before that, there is a little bit about how do you measure measurement of conductance or conductivity. Like if you measure the resistance or the resistivity, you can easily measure the conductance with their each other's inverse, right? So when you have an unknown resistance, like you guys did this in physics, if you needed to measure an unknown resistance, how do you calculate that?
Wheatstone bridge.
Wheatstone bridge, absolutely. Now, can you use Wheatstone bridge in this case, where if it's an electrolytic conductor?
No, you can't do that.
Why not?
Ma'am, because how would you use a Wheatstone bridge across a electrolytic conductor where you need an entire different setup for the like for electrolytic conductors, you need like an entire setup, right? With electrodes, connecting wires and stuff like that.
Wheatstone bridge. Okay, I forgot how you had Wheatstone bridge, but it's something like this, right?
Diamond, and then there is a
There's on,
thing in the middle.
and then beach
Yeah,
one is connected.
there was a galvanometer. Yeah.
And then we have like battery, right?
Hmm.
All of these are like the lines are all wires, and the resistance are represented like this. All I need to do is erase, instead of having like a solid resistor, like instead of putting, I don't know, bulb or whatever, in experiment resistors look like this and you have colored cylinders. Instead of putting this, I can attach these wires. I can just like have some extra wires and then put them in a cell,
Hmm.
right?
Okay, so either way you can use it.
The setup exactly is not the problem. There are other problems why you can't use a Wheatstone bridge.
You use the Wheatstone bridge because the length is same or comparable, right? Of the wires, I'm not sure.
So one reason is you cannot use DC current in experiments with the electrolytic cell.
So, ma'am, right now we're jotting down the reasons why we can't use a Wheatstone bridge to calculate the conductance or measure the conductance of electrolytic conductors.
Yeah, basically. Like it's not
Okay.
exactly why we can't use Wheatstone bridge. It's why we can't use Wheatstone bridge the way like the standard Wheatstone bridge is used. Like the
Okay.
problems that come with using a Wheatstone bridge as it is.
So, but it's only in terms of electrolytic, like ionic conductors, right? We're not talking about metallic conductors.
Only for ionic conductors.
Okay.
So we cannot use DC current when we are doing experiment with ionic conductors, because what is the driving force behind like electrical conduction in this case?
A battery.
Oh, no.
This one, right? The diagram.
Whatever it is, in electrolysis or electrochemical cells, like whatever,
Potential difference.
what is the potential difference affecting, or what is the passage of current causing, or how is it related? What is it being caused by?
No, ma'am, I didn't get it.
So the main thing, like why metal, oh, that's a point we haven't discussed earlier, I'm sorry. Okay. So in the case of metallic conductors, I mentioned that as electricity passes through it, the nature and the composition of the conductor itself does not change.
Hmm.
In the case of ionic conductors, if you keep passing electricity through an electrolyte, like zinc electrolyte, like zinc and copper case me, for example, what happens? Like what does the passage of current cause?
Due to the passage of current, but there's a finite amount of electrolyte which is present, right?
Yeah,
So at one point the reaction will stop.
exactly. And what happens during the reaction is that it changes the nature and composition of the electrolyte itself, of the conductor.
Yes.
Right? Because of the reaction. So if you use DC current, like eventually after a while, like the reaction is gonna stop. You can't do anything with it. So because of this point, yeah, nature of the electrolyte or the conductor itself. Right? So because of this, you cannot use DC current, and because you can't use DC current, you end up using alternating current. So in the Wheatstone bridge, if your source, instead of a DC battery, if you change it to an alternating current source, you can overcome this particular aspect of it. So the passage
Because
of
then the reaction will still happen.
reaction will happen, and alternating current like reverses direction, right?
Mhm.
So it's still going to conduct electricity, and you can maintain the nature, like the composition, for a longer time as compared to like a direct current. Yeah. So that is like a main change, or like main uh, adaptivity, like thing that you need to adapt to overcome your problem. That is the thing. Okay. And another thing, like the way you measure conductivity is, you use AC current, and then you use a special thing called conductivity cell.
So that's for measuring the conductance in ionic conductors.
Yeah. So in order to measure conductance, you need to be aware, like if you look at the formula, you need to be aware of the length and area of cross section, right? Now, how do you define that for a liquid? So in order to fix that length and area aspect of it so that you can plug those values in the formula, you use a specialized setup. So that setup is called a conductivity cell.
Now, okay.
Yeah. Noted?
Yes, ma'am.
We'll get into the designs of conductivity cell and how they use it for measurement.
So, ma'am, to measure the conductance of electronic or metallic conductors, we simply use the Wheatstone bridge using DC current. Simple and easy setup, it can be measured easily. However, for ionic conductors, we cannot use the Wheatstone bridge because Wheatstone bridge uses DC current, whereas because the nature of the electrolyte and composition of it changes during um, while using DC current, and AC current is preferred, so we can't use that. So to measure ionic conductance, we use a conductivity cell, which you will explain now. Okay. Sorry, that was a mouthful.
Like a Wheatstone bridge setup, you just make some changes to it. See, Wheatstone bridge
Okay.
straightforward, right? Resistance, because it's wires ka, you can define the length of wire you're using, and you can area of cross section. But for electrolytic cells, it's not as direct as that. Like the current also you can't use direct current, and length and area also you need to make some adjustments to be able to get the calculation, right? So that is why these are like the modifications. Like one is AC current, and the second is you're designing a conductivity cell so that you keep all your variables proper. So only the electrolyte, if you change, you get like proper values for it.
Yes, ma'am.
Dhriti, Ansh, Shantanu, we move forward.
Yes, ma'am.
And you guys, like, are you following like any questions, any doubts so far? How's it?
No, ma'am.
No? And Shantanu, you guys, like, you all have been really awfully quiet, so just wondering how's it going.
Yes, ma'am, I understand.
Ansh Gupta, can we go like noted or still noting?
Yes, ma'am, done.
Cool. So conductivity cell is used to measure conductivity. So if you recall the formula, conductivity is equal to G into L by A. Yeah. Or 1 by R into L by A, right? So in order to calculate the conductivity of anything, you need to know the length, the area of cross section. So length is basically the length that the electrons will have to travel. Area of cross section is the area of cross section available for them to travel. And resistance you need, like once you calculate the resistance, put it in the formula and you can get the conductivity, right? So these are the things we need to fix. There are two designs that that are pretty popular, commonly used for conductivity cell. One is in this shape, like a horizontal tube. So there is an opening here, so you use this opening to fill your conductor, like the electrolyte, sorry, which needs to conduct. Then the conductivity part of it, okay, you have your electrolyte. Then you use like these specific electrodes. So they're set up like this. And these electrodes are connected here. Now these electrodes, if these are the connecting wires, the electrodes have kind of like the wires have kind of like a covering over them. Okay. So these electrodes are called, like they're called platinized platinum electrodes.
What is that supposed to mean?
So the material that the electrodes are made up of is platinum. Now that platinum metal is covered with a layer of platinum black. So basically it's a different form of platinum. So you have platinum, you like powder it, and then you coat it with a thin layer of that platinum powder over the electrode.
Okay.
And then these, you can further connect it to your connecting wires. You can connect it to your Wheatstone bridge or any other device that you're using this particular cell in. Another design, very similar, just that the shape and the setup varies. So there's a container. As always, you need a container to hold your electrolyte. So instead of this looking like a cathode ray tube, your electrodes are directly dipped in it. So everything else is the same. You're going to have platinized platinum electrodes and all, just that the setup of it is different. So these are your wires, and then you have like the platinized platinum electrodes right at the bottom over here. And these are going to your connecting wires. So these are like designs for your conductivity cell. Components are, so one, you have platinized platinum electrodes. So platinized platinum, because it's inert and it won't interfere with whatever electrolyte you take. It helps with that. So the area of the electrodes, like with area of cross section A, so this particular area, you can see how much area is exposed for conducting like how much area is dipped into the electrolyte. So that much area is available for your conducting the thing. So that would be the area of cross section. And they are separated by a distance L. So the length that the electron will have to travel is the distance between the two conductors. So these two electrodes are separated by the distance L. Again, area of cross section is the whole area of the electrodes available. So that is the whole cross section that the available for the electrolyte to transfer electrons, to pass current through. And the length that the electrons or ions will have to travel is from one electrode to the other. So the distance of separation between them is L. Yeah. So this is the cell setup for the conductivity cell. So whatever electrolyte you want to measure the conductivity for, put it in the container, and the specifications of A and L are like, while constructing the cell itself, like they're fixed. That is the thing.
Yes, ma'am, got it.
Okay. So then, yeah, so the solution is like confined between the electrodes in a column of length L. So this particular solution is there in this column. And area of cross section is whatever is the area of the electrode. So that's, you have your A and L. Then put it in the formula. So if you are using the Wheatstone bridge setup, you will be measuring the resistance. So resistance R equal to 1 by K into L upon A. And from the resistance, you can calculate the K. This is the same thing if you plug it in this formula. Now, because for a particular cell, L and A are constant, right? So that will remain the same physical quantity. If I'm using this particular container, my L and A are fixed. So that particular quantity, L by A, that is specific to a particular conductivity cell, is represented by the symbol G star. This is called cell constant. So the reason why we take cell constant, like why each cell comes with its own G star, that is cell constant, is because you like measuring L and measuring A, like the more number of things you keep for measuring, the more inaccurate your result is going to be. Like one, it's going to be inconvenient because you need to take it apart every time to, measure the thing and then keep it down. And two, the more things you leave for manual this thing, the more inaccuracies there may be.
The more chances of human error.
Not reliable. Yeah, human error. That's it. So that's why for any cell, this particular value L by A is defined as a cell constant G. So the only thing you're changing is the concentration.
So, ma'am, for every type of cell, yeah, the G value will differ, right?
Yeah. So if you're doing a particular experiment, you will be either asked to calculate G star, or you will be given G star, like, okay, for the conductivity cell used, the cell constant is so and so value. Right.
So, ma'am, R can be G star by K as well.
Oh, yeah. Yeah, you can play around with this, have different formula. So G star is L by A. So R will be equal to G star by K. Or you can also call like cell constant is equal to the resistance into the conductivity, R into kappa. Yeah, note down these formula. You may, like, these kind of cases, you can completely do away with L and A. So if you know the resistance and the conductivity, you can calculate what is the cell constant. What else do we have about cell constant? Then we have its relation with the concentration. Okay. What I'll do is we'll discuss all the theory today, and then tomorrow. Okay, how many of you will be attending online session tomorrow?
Ma'am, what time do we have the online session? I mean, either way, it's fine. Can we have it early in the morning?
Oh, please let me sleep.
Yeah, we're not
No,
gonna.
not like 7 o'clock, 8 o'clock, like 10 o'clock.
Yeah, 10 to 12
Ma'am,
or 12 to.
I don't think the 12 to 12 works for me. I think this time only afternoonish.
No,
It's
no,
fine.
no, 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 no.
No, but like
Sunday afternoon, no, dude, what is
yeah.
wrong with you?
Yeah.
Just
What do
get
you
it
mean?
over with in the morning.
Sunday is supposed to be a free day, but we do have class, and class get over by maximum by lunch, and it's really good for everybody.
If you have it in the middle, it's going to be like, okay, you can't do anything in the morning or you can't do anything.
Yeah, or in the evening, like we can't plan anything.
Did sir announce physics tomorrow at any point of time? Like,
No, ma'am,
No.
he hasn't.
okay,
But ma'am, can we do chemistry, because in class we've started with chemical kinetics. We
Yeah,
still
yeah.
have
Yeah,
like a
and
bit
physics,
to
we
do.
are way ahead of portion.
And we are missing next week a class.
Yeah, next week our class, correct.
I want to take that. No, because if sir is going to take, then timings also, like I'll have to speak to him about that. It will be a 4-hour
He
class.
hasn't given anything, like he
I-
hasn't mentioned anything.
I'll take 10 to 2 in case physics class is also going to happen, then it will be, yeah,
And ma'am, if only your class is going to happen, then 10 to 12.
10 to 12, yes.
Okay.
Can't we have it like earlier? 9 o'clock to start, 9 to 1. Get over by
Completely fine
lunch.
with it. 9 to 12 or 1. Yeah, 9 to 1, right?
9 to 1, 2 hours physics, 2 hours chem. And if
If
no
we have
physics,
both of them, yeah, then 9
yeah.
to 11.
And then if no physics, then 10 to 12 is okay.
Agreed.
All right. Ansh, Shantni will be attending, right?
Ma'am, why I was saying afternoon because I already have something planned for morning. But okay, if everyone says morning, then it's fine.
Okay. Okay. Shantni,
Thanks, Ansh.
what about you?
Thank you, Anj.
I'll be
Appreciate your
attending.
sacrifice.
Shantanu, what about you?
You're
I'll
welcome.
be attending.
Okay. All right. Cool. So we'll be practicing things related to conductivity, conductance, and relation with concentration, molar conductivity, and all. We'll do it tomorrow. Okay.
We done for today?
Molar conductivity, I'll just discuss the definition of it. Just a term, like continue with this thing. So molar conductivity is represented by or denoted by the symbol. It looks like this. So this is lambda. So you have like capital letters, small letters, right? So capital lambda looks like this, and the small lambda looks like this. Again, Greek alphabets stands for L. Yeah. So can you guess what is the meaning of molar conductivity?
In terms of electrolyte, ionic conductance.
Molar matlab, yeah, ionic. Like everything we're studying right now is relevant only for ionic conductance. Conductivity hai.
Based on concentration.
Yeah. So it is conductivity for 1 mole. So conductivity divided by the concentration. So concentration usually expressed in moles. So yeah, like molar mass is the mass of 1 mole of atoms or molecules. Molar conductivity is the conductivity of 1 mole. So it's conductivity divided by the concentration. So in this case also, you need to be very careful with the units. concentration, if you take it as moles per liter, like meter cube, that, and then conductivity also, like is it in centimeters, meters, that you need to ensure that all your units are uniform.
Molar inverse.
The variation, we will, like the graphs for strong electrolytes, weak electrolytes, that part we'll do it tomorrow. Okay. Right now,
Okay, ma'am.
sum up all the things, like all of the formulas and things that we learned related to conductivity. Okay. So first we came across conductance. So conductance is the opposite of resistance, denoted by G is 1 by R, inverse of resistance. So that is also equal to A upon rho L, which you can write it as conductivity into A by L. Okay. So conductivity here is inverse of resistivity, also called specific conductance. Conductivity K equal to 1 by rho. यहाँ से फिर substitute and write it. So the relation between, so G will be equal to K into A by L. Then we came across this quantity cell constant. So when we apply these formulas for electrolytes specifically, the quantity A by L is defined by this thing called cell constant, denoted by G star, that is equal to L upon A. So applying it to this particular formula, G equal to K into A by L, or 1 by R equal to K into 1 by L, this is also equal to resistance into the conductivity, or resistance conductivity upon conductance. It's just figuring out different permutations, combinations of the same thing. Like G star equal to L by A is a definition. A by L is equal to G upon K. So L by A will be K upon G. And G and 1 by R, they're inverse of each other. So that's how you get these formulas. Just rearranging different permutations, combinations from the relations we have. Okay. Then we spoke about molar conductivity. That is conductivity per unit mole. So that's mole matlab concentration. So this is represented by lambda m. The m represents the fact that it's for 1 mole, molar conductivity is lambda. Okay, so these are like the major.
Yes, ma'am, got it.
Yeah. One thing you can like whatever question you get, figure out what stands for what. Like if you get, okay, interpret, is it G, is it R, is it G star, is it molar conductivity? Once that interpretation is done, you can directly apply the formula. Another thing you need to take care of is, are the units matching or not? That's the thing you need to take care of.
So all of them should be in SI units for us to solve it, right? Or in comparable units. Okay.
It's what you've been doing in physics also. Like you can't divide meter by centimeter. You need to convert meter into centimeter or centimeter into meter, right? That way. You can't add 1 meter plus 1 centimeter. You can't call it 2. Like you need to convert either of them. Same
Yes, ma'am.
Ensure that your units are uniform. Okay. Revise it. So we'll do, like, do you guys want to go through the topic practice for this section?
Can we try it, and then when we finish molar conductivity, we can, like, can we try it at home, and then tomorrow, if we have doubts, we can come?
Yeah, absolutely. Like all of you have, like if you don't have the book, let me know. I'll share the PDF. Otherwise, go through the questions, get familiar with it. Tomorrow we'll discuss the variation and solve all the problems. Okay.